We have now seen how a p-n junction diode operation changes when we apply a voltage to it. Let's take this a step further and learn how to plot the current voltage characteristic of a p-n junction diode in the dark. Let's start with a short recap. In this slide you can see our now familiar p-n junction with a voltage applied to it. This particular diode is under forward bias. This means that the voltage applied to the p-type region is positive with respect to the n-type region. A significant current flows through the diode. The current leaves the n-type region of the diode through the cathode into external circuit and enters the p-type region through the anode. So the question is, how can we determine the value for I, the current, for a given applied voltage VA? This relationship of the p-n junction diode is called the IV relationship, and it is an important relationship for any electrical device. Before we show the equation and how to plot this relationship, let's quickly remember what happens conceptually in different voltage bias conditions. In forward bias conditions, the depletion region in the diode shrinks. Consequently, the electrostatic potential across the depletion region decreases, allowing the diffusion current to dominate. This essentially turns the diode into a conductor and allows current to flow through the diode easily. As we increase VA in the forward bias direction, the current will increase exponentially. In reverse bias, on the other hand, the depletion region is expanded. Now the drift current dominates and a very small amount of current will flow in the opposite direction as in the forward bias. This can be seen by the profile of the quasi-Fermi levels in the Venn diagram that do indeed slightly change from the p-type region into the n-type region. The slope and the area between the quasi-Fermi levels is an indication of the direction and amount of current flowing through the diode. The profile, the direction of slope, and the area between the quasi-Fermi levels is notably different when compared to the forward bias condition. Now we are almost ready to move to plotting the characteristic curves. You may have noticed that the title of this video is the dark JV, but so far in this video we have been explaining the IV characteristic of a diode. You should remember from earlier videos that I represents current and J represents current density or current flowing per unit area. The only difference between JV curve and IV curve is that J equals I divided by area. Since the area of a diode is constant, the shape characteristic of these two plots are identical. Since we deal with solar cells in this video series, we will now switch from I to J. Once we start discussing illuminated solar cells, characterization per unit area makes a lot more sense. So we will now switch to J. So here is our axis ready for plotting. This is a semi-logarithmic plot where the y-axis shows the current density on a logarithmic scale, while the x-axis shows the applied voltage on a linear scale. On the right side of the plot, we have the forward bias region. Let's plot the current density. We can see that the current density exponentially increases as we applied a forward bias. It looks fairly linear in this plot, but that is because this is a semi-logarithmic plot. Now let's look to the reverse bias region. When we plot the current density there, you can see that there is a small amount of current. It is important to note that this current density is actually negative. and is only positive in this plot because of the fact that the y-axis is logarithmic. Rather than exponentially increasing at negative biases, this current density actually approaches the dark saturation current, G0. And G0 is a very important parameter of solar cells, and we will be discussed in detail in a later video. This JV characteristic can be written using the Shockley equation. In this video, I will simply give you this equation, and that may be enough for most engineers working in this field. However, there is a bonus video that you are free to watch to understand the full derivation of this equation. Let's take a look at some consequences of this equation. We can see that if applied voltage is 0, it means VA is 0, the exponential term will reduce to 1, resulting in a current density J of 0. No net current flows through a diode. As VA moves in the positive direction towards infinity, J exponentially increases. As VA moves in the negative direction towards infinity, the exponential term reduces to 0 and J becomes negative and reaches J0. It should be noted here that this is only the case for an ideal diode. In reality, there is usually a negative breakdown voltage where the diode will start to conduct large amounts of current in the reverse direction. However, solar cells do not typically operate in this regime, so we can ignore that part of the JV characteristic. It is good to see what the dark JV curve looks like in a linear plot. You will likely see it represented this way as well. Here you can see that it is very difficult to discern the negative current density, J0, in the reverse bias region. This is because G0 is usually on the order of femtoamperes per square centimeter, compared to the milliamperes per square centimeter shown in the forward bias region. You can clearly see the exponential increase in the forward bias region. This exponential shape will become very important when we start looking at how this curve changes when the diode is under illumination. This will be the topic of the next set of videos.